G'day viewers. In this episode we're going to walk through 4 simplified examples of how to measure cyber risk utilising Testimation technology. One does not measure cyber risk directly, one measures cyber confidence first. This is the direct measurement we make. Only after executing this direct measurement can we execute the indirect measurement of cyber risk via the cyber risk equation. In this episode, we investigate the cyber risk associated with being connected to a large information network. The cyber risk prediction and measurement construct embedded in Testimation technology has been experimentally validated to greater than 98.07% accuracy, and all experimental results are available for peer review. The Testimation technology solution utilised within this episode is commercially available and has undergone a rigorous development and validation regime prior to commercial use. An effective means by which to communicate the decision-making power of Testimation technology is to answer some obvious questions utilising several simplified examples. In this episode we're going to investigate number 1, the cyber risk associated with a full spectrum port attack. Number 2, the cyber risk associated with a primitive brute force attack. Number 3, the cyber risk associated with internet banking. And number 4, a Splunk Phantom example. Let's now look at the first simplified example, that is, the residual cyber risk associated with resisting a full spectrum port attack. Appearing on screen is the at-risk graphical user interface. We shall utilise this GUI to measure our cyber confidence. To perform a measurement, we only need to enter 2 inputs, that is, the number of test scenarios we expect to execute and the number of vulnerabilities we are testing against, that is, in our case, the total number of ports. In our simplified example, we shall graphically visualise our port vulnerabilities against 91 Open Web Application Security Project test scenarios. Let's assume that one of those 91 test scenarios calls for all ports to be deactivated, including the reserved ports. The quality assurance objective for this specific test scenario is to confirm that the port deactivation function operates correctly. Therefore, if all transmission control protocol and user datagram protocol ports are tested and confirmed to be inactive, how secure is my computer against penetration from remotely located external actors? Step 1. Input the number of test scenarios we expect to execute in the overall quality assurance solution. Although we are only testing against one specific OWASP scenario in our simplified example, we shall enter 91 into the at-risk GUI. Entering 91 test scenarios rather than just one enables us to graphically visualize our vulnerabilities against the complete quality assurance solution rather than just one element of it. Moreover, it assists the viewer learning experience. Step 2. Input the number of vulnerabilities we are testing against, that is, 65,536 TCP ports plus 65,536 UDP ports equals 131,072 ports. Step 3. Our cybersecurity confidence is measured to be 99.83%. Hence, utilising the cyber risk equation, the cyber risk associated with this specific test scenario is measured to be 0.17%. This means that the residual cyber risk associated with successfully resisting a full spectrum port attack is 0.17%. In other words, if all ports are deactivated to resist the possibility of a full spectrum port attack, then a 0.17% probability remains that our computer system may still be breached by alternative means, for example, sabotage or espionage. An important feature to appreciate is the normal distribution curve appearing on the right-hand side. The darkly shaded area at the centre of the bell curve, associated with dimension beta, denotes the extent to which an infinitely large computer system is actually being tested. The graph shows us that from the perspective of statistical mechanics and probability theory, these 91 OWASP test scenarios span 65.99% of an infinitely large computer system, as long as the computer system is typically connected to the internet. Thus, any smart device connected to the internet is at the centre of an infinitely large computer system. Why is it at the centre? Well, the answer to this question is very simple. Where is the centre of an infinitely large sheet of paper? Where is the centre of the universe? The answer to both of these questions is that the centre is everywhere. Therefore, any smart device connected to the internet is at the centre of the information universe. This centrality is the reason why the statistical mechanics and probability theory built into Testimation technology is able to measure cyber risk. Another important feature appearing on the graph, associated with dimensional row, is the lightly shaded area which denotes system vulnerabilities, that is, the total number of ports to be individually tested. However, if the quality assurance objective has been achieved, then the lightly shaded area denotes the cybersecurity confidence. As a generalization beyond this simplified example, we can say that when the lightly shaded area extends beyond the darkly shaded area, then the quality assurance solution achieves 100% coverage of the required testable scenarios. Or in other words, it achieves 100% coverage of any new software development associated with a project. That is, 100% of newly developed code will be quality assured. Okay, let's now move on to our second simplified example. Once again, we shall utilise the at-risk functionality. In this simplified example, we are asking the question, what is the cybersecurity confidence associated with a primitive brute force attack on a user login function, utilising the Oxford English Dictionary as the test basis? Step 1. Input the number of functional processes we expect to execute in the overall quality assurance solution. In our case, it is just one function. Step 2. Input the number of vulnerabilities we are testing against, that is 171,476 words in our simplified example. Step 3. Our cybersecurity confidence is measured to be 99.97%. Hence, utilising the cyber risk equation, the cyber risk associated with this specific test scenario is measured to be 0.03%. This means that the residual cyber risk associated with successfully resisting a primitive brute force attack in English is 0.03%. Thus, if 171,476 words from the Oxford English Dictionary were entered into the user login function and they were all rejected, which means they all passed the quality assurance phase, then a 0.03% probability remains that the user login function may still be breached by alternative means, for example, foreign language words. For our third simplified example, we shall utilise Testimation 1 functionality. Our quality assurance objective is to determine the number of test cases required to deliver internet banking functionality, satisfying the conditions cyber risk is less than or equal to 1% and cyber confidence is greater than or equal to 99%. It is important to mention that we obtained the information we are going to enter in 2018, so the actual values today may differ. Step 1. Input the number of functional processes within the internet banking environment. In my personal internet banking environment, we counted 120 functional processes. This means that we counted 120 user pathways through the internet banking GUI. Step 2. Define the approach to testing. This is done by selecting one of the calibration factors, as appears on screen. Our approach to testing will be to validate all critical, high, moderate and low priority test cases. If we had have selected the 0.75 calibration factor, we would be stating that our approach to testing is to validate all critical, high and moderate priority test cases only. In other words, we would be neglecting low priority test cases. We may decide to adopt this approach for a variety of reasons, for example, project delivery constraints. Similarly, if we had have selected the 0.5 calibration factor, we would be validating critical and high priority test cases only. Step 3. Select a risk quotient value. The default value is 0%. However, users such as quality assurance managers, project managers and business owners are able to specify a level of additional cyber risk that they are willing to accept in order to compress the project timeline and hasten project delivery. Consequently, as the value of risk quotient increases, the number of test cases to be designed, written and executed decreases, which of course saves time and money, but comes at the expense of quality. Step 4. Input the average number of test steps per test case. In order to achieve this, we need to do some work. We will need to empirically establish this value within the internet banking application, or we must have access to historical information. In our case, we actually executed 120 functional processes and empirically measured that the average number of test steps per test case is 5. The average number of test steps per test case may vary depending upon the testing phase. For example, system testing, system integration testing, end-to-end testing, or user acceptance testing. A good rule of thumb for the average number of test steps per test case for any application is somewhere between about 5 to 10. For typical application end users like yourselves, an average of 5 steps per test case is a good guess because commercial applications should be simple to use. If they are not simple to use, people will abandon them. That's why an average of 5 steps per test case is a good guess. It keeps the user experience relatively simple. Step 5. The number of test cases required to be designed, written and executed with a 100% pass rate is 3,185. Thus, 3,185 test cases need to successfully pass the quality assurance phase in order for the probability of a hidden defect evading detection to be less than or equal to 1%. In other words, if we successfully pass 3,185 test cases, then our cyber risk will be less than or equal to 1%, and therefore our cyber confidence will be greater than or equal to 99%. The obvious question now becomes, is this 3,185 test case estimate correct? Well, having worked on internet banking projects with multiple major banks, we know from commercial experience that the actual answer is approximately 3,000 test cases. So yes, the estimate appearing on screen is quite correct for a 120 functional process application. One feature we wish to draw your eye to is the organisational risk exposure indicated on screen. As with our first simplified example, the graph shows us that from the perspective of statistical mechanics and probability theory, these 120 functional processes span 72.67% of an infinitely large computer system, as long as the internet banking application is typically connected to the internet, which of course by definition it needs to be. Before we move on to our last simplified example, we will reiterate our net position with respect to internet banking. Designing, writing and executing 3,185 test cases with an average of 5 test steps per test case yields a 99% probability that the deployed solution is defect-free if all test cases pass. Okay, let's now talk about Splunk Phantom. Splunk Phantom is a cybersecurity workflow automation tool. In this simplified example, a security operations center is transitioning to the Splunk Phantom platform, but the security operations center team has limited quality assurance experience. Therefore, how many test cases do they need to execute in order to test the playbook shown on screen prior to deploying the automated cybersecurity solution? Let's begin by laying out some essential playbook facts. 5 informational flow pathways are drawn from start to end. The Security Operations Center team quality assurance architecture utilizes agile methodology. Hence, the Security Operations Center team communicate in terms of acceptance criteria. To help you understand what acceptance criteria means in the context of Testimation technology and in relation to our previous simplified examples, one acceptance criteria is equivalent to one test step. Similarly, one test step is equivalent to one dynamic information test. Thus, one acceptance criteria is equivalent to one dynamic information test. The Security Operations Center team have estimated or counted an average of 17 acceptance criteria per informational flow pathway. Okay, the next thing we shall do is partake in a necessary diversion which the Security Operations Center team will need going forward. On screen you can see a decision assistance table constructed utilizing Testimation technology. The decision assistance table demonstrates that test effort increases as cyber risk tends to zero. So, which quality assurance solution should the Security Operations Center team apply? To answer this question, the Security Operations Center team need to recognize that each informational flow pathway from any playbook requires a minimum of 2 test cases, that is, one testing for success and one testing for failure. In other words, one positive and one negative test case respectively. Thus, by inspection of the decision assistance table, QA solution 1 and 2 may be eliminated from consideration. Therefore, the Security Operations Center team must choose QA solution 3 or greater. Okay, let's now input our boundary conditions into the Testimation technology application. For our fourth and last simplified example, we shall utilize Testimator 1 functionality once again. Let's begin by entering the appropriate information. Step 1. Input the number of functional processes. In our case, the number of functional processes equals the number of informational flow pathways, that is, 5. Step 2. Select the appropriate calibration factor. In many commercial environments, quality assurance teams are often pressured into minimal quality assurance solutions. Thus, the Security Operations Centre team decides upon a critical priority test case approach. We will circle back to this decision for a brief discussion shortly. Step 3. Select the appropriate risk quotient. The Security Operations Centre team understand that their critical priority test case approach enlarges cyber risk. Thus, they have decided not to introduce additional cyber risk. Hence, they shall utilise the default value of 0%. Step 4. Input the number of dynamic information tests. Please recall that one acceptance criteria is equivalent to one dynamic information test. Thus, we enter 17 dynamic information tests as shown. Step 5. The minimum number of test cases is calculated, that is, 10 test cases. Let's circle back to the Security Operations Centre team decision to target a critical priority test case approach. As already mentioned, in many commercial environments, quality assurance teams are often pressured into minimal quality assurance solutions. To overcome this challenge, we may utilise the graphical output appearing on screen to specify the optimal quality assurance solution from the decision assistance table we saw on the previous slide. From the graph, we can see that dimension alpha is much greater than dimension beta. Hence, the risk mitigation is much greater than the organisational risk exposure associated with the transition from manual to automated workflows. Therefore, QA Solution 3 from the Decision Assistance table denotes the optimal target solution such that the risk exposure equals 17.69%. This denotes the organisational impact of workflow changes. The risk mitigation equals 80.22%. This denotes the cyber confidence and consequently the test coverage. The cyber risk equals 19.78%. This denotes the testing not executed. In other words, the Security Operations Centre team is carrying a 19.78% probability that they have missed defects. The obvious question now becomes, is 19.78% cyber risk too much to carry? Well, that's a business decision, not a quality assurance decision. Multiple commercial justifications may exist for carrying 19.78% cyber risk. For example, the deployment of an emergency cybersecurity hotfix. Let's now summarise what we have learned. In this episode, we walked through 4 simplified examples of how to measure cyber risk utilising Testimation technology. So, what did we learn? Number 1. In our first simplified example, we learned that if all ports are deactivated to resist the possibility of a full spectrum port attack, then a 0.17% probability remains that a computer system may still be breached by alternative means, for example, sabotage or espionage. Number 2. In our second simplified example, we learned that if 171,476 words from the Oxford English Dictionary were entered into the user login function and they were all rejected, which means they all passed the quality assurance phase, then a 0.03% probability remains that the user login function may still be breached by alternative means, for example, foreign language words. Number 3. In our third simplified example, we learned that if we successfully pass 3,185 functional test cases with an average number of 5 test steps each within an internet banking environment, then the residual cyber risk will be less than or equal to 1%, and therefore our cyber confidence will be greater than or equal to 99%. In other words, the probability of a hidden defect evading detection will be less than or equal to 1%. Number 4. In our fourth simplified example, we learned that transitioning to Splunk Phantom involves quality assuring playbooks. Moreover, the level of quality assurance required by each playbook is guided by the decision assistance table generated utilizing Testimation technology. In addition, graphical visualization techniques are utilized to specify the optimal quality assurance solution from the decision assistance table. Consequently, it was determined that the optimal quality assurance solution carries a 19.78% probability of hidden defects. Let's now close out this presentation with supporting scientific literature. Encompassing the list of scientific literature appearing on screen, a precise and unambiguous mathematical definition of cyber risk is developed, yielding an experimentally validated solution demonstrating how to predict and measure cyber risk for any internet-connected information system to greater than 98.07% accuracy. Moreover, it is shown that the solution holds for all scales of Internet-connected information systems, from an application level to an enterprise level. In addition, it is shown that test effort estimation quantifies cyber confidence, which in turn quantifies cyber risk. Hence, test effort estimation is a mission-critical activity when formulating cyber risk management strategies and may be utilised prior to project commencement, in flight or post facto as an assessment and/or auditing tool. The test effort estimation model construct developed is a statistical-based methodology whereby the evaluations/decisions made result in the contraction or expansion of the Z-score associated with an infinite population of database records. The primary advantage of this approach is that very little information is required client-side at the engagement stage in order to produce peer-acceptable estimates of the required test effort and to accurately predict and measure the associated cyber risk. This approach empowers clients and service providers to precisely define whatever level of cyber risk is to be contractually delivered, capable of being absorbed or prepared to be absorbed by consensus. With the aid of a decision table, estimators are able to articulate and convey to the appropriate authorities various levels of cyber risk commensurate with the available resources. The test effort estimation model construct developed presents an experimentally verified methodology cognizant of commercial realities, yielding the following key advantages. Number 1, it requires minimal inputs. Number 2, it has a scientific foundation. Number 3, it facilitates operational decision making. Number 4, it quantifies risk-based testing. Number 5, it is simple, robust, flexible, consistent, reusable and transparent. Number 6, it is capable of scaling a projected solution from a known solution. Number 7, it embraces continuous improvement processes. Number 8, it confines perceptual subjectivity predominantly to 3 variables. Number 9, it commercially exists as an off-the-shelf product. Well, that's the end of our presentation. Please reach out to us for more information.